Hello, folks. Section 5.6 is on the law of sines. So far in chapter 5, we've been very limited to right triangles. Sine, cosine, and tangent, cosecant, secant, cotangent, those trig ratios deal with comparing the sides of a right triangle, right? Opposite over hypotenuse, adjacent over hypotenuse, etc. What the law of sines is going to do for us is allow us to calculate things and solve triangles that don't necessarily have that 90-degree angle. Before we get started, just to be clear, recapping something from geometry, we discussed this earlier, but just so we're on the same page, if I have a triangle and I call its angle measures HMC, we use capital letters to talk about points in geometry, and those vertices are considered points. And then the sides opposite of those vertices are going to be lowercase HMC, standing for the sides. So going forward, if I ask you to solve a right triangle, it's going to be, the letters correspond to one another with capital and lowercase. Okay, going forward, we have this circle here with two inscribed triangles. The way I have it is, instead of calling, you see A prime C, that length there, instead of calling that diameter, which it is, I'm going to refer to it as 2r, 2 times the radius. So if you can tell, there are two main differences between these triangles. One of them is that the lighter triangle, A prime BC, is a right triangle, and it also goes through the center of the circle, meaning its hypotenuse is the diameter, or 2 times the radius. The other triangle, ABC, is just all kinds of random things there. So the idea is that if we use our trig, so sine, cosine, and tangent, to discuss that right triangle, perhaps there's a way using our circle properties that we can also understand those same ratios by using triangle ABC. The first thing to note is that both of those triangles intercept the same arc. They both intercept arc BC. That means that angle A prime must be congruent to angle A. And that's just from geometry properties there. And if those angles are congruent to each other, then that means the sine of A prime must also equal the sine of A. And if that's the case, let's actually write what the sine of A prime is, because that's a right triangle, so we know how to set up that ratio. The sine of A prime is equal to opposite over hypotenuse. So opposite of A prime, we have the side A, over the hypotenuse, we've labeled as 2r. So if that's the sine of A prime, and we know it is equal to the sine of A, then that also implies that the sine of A must also equal A over 2r. Now, another way that we can rewrite that equation right there is if I go ahead and multiply both sides by 2r, multiply this side by 2r, then I end up with the sine of A times 2r equals A. And then if I try to get my variables, we'll try to get the A variables on one side, leave 2r alone. If I divide both sides by the sine of A, then I end up with this equation, 2r equals A over the sine of A. And we're going to let this just hang out here for a second. Right now, that doesn't really seem like you've accomplished much, but in actuality, it accomplishes a lot, because all we did here in this circle with these circumscribed triangles was we took angle A, and we slid it around the circumference to create point A prime. And we used those properties of circles, knowing that those inscribed angles were congruent to each other, and proved that whatever was true for the right triangle for angle A prime would also be true for the oblique triangle with angle A. So what we could do is, and we're not going to take the time to do it, but if we were to take point B and point C and also slide them along the circumference of the circle, to where if we were to stretch them out and create right angles between, or at angle A and at angle C by drawing diameters through angle B and angle C, then we would find that angle B and angle C have these same properties as angle A prime does. It would be the same as B prime and C prime that we would make it. So you could look up a full proof of it if you want. Just know that exactly what we had here with the sign of A and A prime is going to be the exact same scenario for B and B prime, which means B over the sine of B, using what we learned up here with A and sine of A, would also end up being 2r, because we'd create it into a right triangle with the sine of B prime. And that would also mean that C over the sine of C would equal 2r. So you're going to notice, this is very important, if all of these are equal to 2r, then mathematically speaking, if these three things are equal to something, then that also implies that they're equal to each other. So that implies that A over the sine of A must equal B over the sine of B, which must also equal C over the sine of C. And this string of proportions right here is called the law of sines. The law of sines. Particularly, we're going to use the law of sines to solve for sides and angle measures in triangles. Now, from geometry, you might recall congruence theorems that we used to prove that triangles were congruent. Particularly, one was called ASA and the other was called AAS. These were called congruence postulate. So it's just saying if you have two angles and the included side of a triangle and they're congruent to the two angles and included side of another triangle, that implies that the triangles are congruent to each other. Same thing if you have two angles but a non-included side is congruent to that of another triangle, then that means the triangles are congruent. In other words, this implies if we have the cases of ASA and AAS, that there's only going to be one unique solution. And that's important because when I use the law of sines to solve, I know that in these two cases right here, ASA and AAS, I know that I'm only going to get one answer. Okay, that's not always going to be the case. And in the next section of our video, we're going to talk about something called ambiguous cases. So for now, we're just going to do a couple of examples where we know we're going to get these unique scenarios. So examples. For each of these examples, the directions are simple. You are going to solve triangle ABC. So that means whatever information is given, you have to fill in the rest. So I'm looking for 3 angles and 3 sides for every single triangle. So for number 1, if I tell you that angle A is 30 degrees, B is 100 degrees, and little a is 15, I want you to solve this triangle. So first thing we might do is go ahead and draw a triangle. Again, they're not necessarily right triangles, and we're going to label it accordingly. So it's okay if your numbers don't necessarily match your triangle. It doesn't have to be drawn to scale because the algebra will still work. But since it looks like this angle's biggest, I'll call that one B, which is 100 degrees. I'll call this one A, which is 30 degrees. And then the side A is going to be across from that 30 degrees, so this must be 15. So I'll call that C, I'll call this little c, and I'll call this little b. So the idea is that we need to solve for the 3 remaining parts of that triangle. First thing that comes to mind for me is the angle. I know that the 3 angles of every triangle should add up to 180 degrees. So if I know 2 of them, then I'm just going to take 180 minus 100 minus 30, and that's going to give me 50. So that gives me the first missing part, is that C will equal 50 degrees. Okay, from there we can use the law of sines to help us figure out the sides. So if I have A over the sine of A, now when you use the law of sines, you don't have to use all 3 ratios. You could just use 2 of the ratios that you need. A over the sine of A, I already have, and then I have A and a side length, so I need to solve for either B or C, so just choose one. So I'm going to say that that equals B over the sine of b. And this implies, let's fill in what we know. We know little a is 15 over the sine of 30 should equal, we don't know little b, so I'm going to leave that variable there, over the sine of 100. And then the goal is to try to get the variable by itself. So if I multiply both sides by sine of 100, I should isolate my variable. So when I do that, I'm going to end up with, I'm going to switch these sides here so that b is on the left side. So if I get b is equal to 15 over the sine of 30 times the sine of 100. Now technically the sine of 100 is over 1, so I could, when we multiply fractions, we multiply straight across. So I could make this into one giant fraction, which would be 15 times the sine of 100, all divided by the sine of 30. Ensure that your calculator is in degree mode, and then when you type that in, you should end up with b. Let's round to the nearest tenth for this video. We'll say that b is approximately 29.5. Okay, so that solves for b, and now we need to go find c. So to find c, you could use the b angle on side length, but basically anytime you round, you get further and further from the true answer. So I would go ahead and stick with using a and the sine of a, since those values came from the problem, and use that to find side c, so c over the sine of c. So this implies, if I fill in my information again, I also have 15 over the sine of 30, is equal to c, which we found earlier, remember, was 50 degrees. So technically this angle here is 50. Oh, I'm sorry, the side length though I still don't know, so it's going to be c over the sine of 50. And then I'm going to go ahead and multiply both sides by the sine of 50, leaving me with c is equal to 15 times the sine of 50 over the sine of 30. And again, when you plug that in your calculator, round to the nearest tenth, you should get c is approximately 23. And those are the three missing parts of the triangle: side c, or sorry, angle c, side b, and side c. So that's how you solve the remaining part of the triangle. Let's do one more. Example 2. If I tell you that angle A is 33 degrees, angle B is 105 degrees, and side B is 37.9 degrees. Again, let's draw a triangle to represent this scenario. So I'll say this is 105 because it looks the biggest, so I'll call that angle B, and I'll call this 33 for angle A, and then we know side B is 37.9, so let me call this angle C, this side A, and this side C. This is just coincidence that I gave you angle A and angle B. You won't always have those two. You might be given angle C sometimes as well. Okay, again, first thing that's easiest for me is to find that missing angle. I know the three angles should add to 180, so 180 minus 105 minus 33 will equal 42. So off the bat, we know angle C is equal to 42 degrees. Okay, then I need to solve for the missing sides. So you can use, let's see, I know for sure my B values, so that's going to be a great place to start. I know B over the sine of B, so let me use that to find something else. Let's do A over the sine of A, which is 33. Oh, I guess I just could have left that. It's okay, let me fill in the rest of the information. So B over the sine of B is going to be 37.9 over the sine of 105, and that's going to equal A over the sine of A, which I already said was 33. And if we're going to isolate that, we'll multiply both sides by the sine of 33, leaving us with A is equal to 37.9 times the sine of 33 all over the sine of 105. And when we do that, we're going to end up with A is approximately 21.4. And make sure you're checking these calculations too as you watch this video. Don't just take for granted that I'm doing it correctly. Make sure that you'd be able to do it correctly too. Make sure that you're comfortable plugging that stuff into the calculator as well. Okay, I'm going to continue using the b's since I know those. So b over the sine of b is going to equal c over the sine of c. This implies that 37.9 over the sine of 105 is equal to, I'm looking for side C over the sine of, remember we found angle C earlier here, so that's the sine of 42. And if I go ahead and multiply both sides by the sine of 42 to isolate the variable C, I end up with C is equal to 37.9 times the sine of 42 over the sine of 105, which is going to give us a value of C to be approximately 26.3. So that's the law of sines, using a little bit of information, what you know about a triangle, to find the missing information, particularly when you are given two angles and a side that's not included, or two angles on the side that's included. Either way, you're going to get unique solutions, which is why everything worked out lovely in this video. The next video is going to talk about the next section, which is called ambiguous cases.